using the carbon gas?
Okay. This is Maria Paula Angarita. She's a senior physics major, and the summer before last she did an RU at Vanderbilt in biophysics, and last summer she did an RU at MIT, and she's going to tell you about it. So here she is.
Hi guys, my name is Maria Paula. I'm here to present the research I did at MIT this summer. No? Okay. And I was in the Herrero group at MIT. They are condensed matter experimentalist group in the physics department. And here's an outline of my talk. I'm going to go over a not so brief background on topological insulators. The title of my talk is Photocurrent generation in topological insulators, and specifically we're going to look at bismuth selenide. So I'll go over a background. It's not going to be so brief because it's I think to understand the concept is really, and there's really cool physics going on here, so it's very important. So I'm going to spend quite a bit of time there. I'm going to link the topological insulator bismuth selenide to graphene, which is a huge hot topic in condensed matter nowadays, and the photothermoelectric effect, which is important for the research that I did this summer. I'll go over very briefly the fabrication of the devices, the experimental setup, and some data and results, and I'll conclude the questions. Please ask me questions. Like, I don't want to be here just talking. Yes?
What is the meaning of topological data?
Yeah, I'm about to answer that.
Okay.
Okay. So, for now, I want to put the name aside for a second, the topological insulators, and I just want to point out that in condensed matter experiment, what physicists are concerned with is trying to study the electronic behavior of different materials. So how electrons behave in thin films of X, Y, or Z material. And the purpose of that is to either gain insight into fundamental physics going on in the material, or if we already know the physics, to find applications of it. And that's more engineering, but there's a lot of money in this field, and that's what physicists are concerned with. And so the topological insulator, what it is a material. And it's a material that has matter that is in a very special quantum mechanical state. And basically, what's so special about it is that the electrons in the lattice behave as massless fermions. So relativistic physics applies here. And there's a lot of very interesting results coming out of that. So that's one of the reasons why they're very interesting. They also have very interesting spin physics because they behave like relativistic fermions. The electrons have interesting spin physics, which just means that there's this like really unique, very unique consequence of the fact that the spin of the electron interacts with its own orbit. And that's due to the fact that the topological insulators are usually very heavy materials. And so the spin of the electron couples with the orbit of it, the orbital angular momentum, and that leads to like really weird electronic behavior. And because there's interesting spin physics going on, a lot of engineers are excited about topological insulators. They have a lot of potential in like the next generation of transistors or lasers, or the next generation of technology. And it's also being looked at for quantum computing and quantum information. So that's why, like, I guess, engineers think it's cool, or people who apply stuff. And I think one of the main reasons why physicists are looking at topological insulators is because they're very fertile ground to look for the Majorana particle. I don't know if I pronounced that right, but this particle is a non-fundamental fermion. It's a fermion, which, like any other fermion, has a half spin, integer half spin. No, not integer, sorry, a half spin. But what's really special about this particle is that it's its own anti-particle. So whenever you see a Majorana particle, it annihilates itself. And the reason why that's really, 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 really hot in physics is because there's a link with superconductivity. So actually, topological insulators are being experimented on along with superconductors, and they're seeing what kind of results come out of that. And also something that's really weird that I'm not. By the way, this is not something I'm going to go into. It's not directly related to my research, but I think it's something that's cool to know. Also, the these Majorana particles do not obey Abelian statistics, which means that normal wave functions and positions and all these things that we use for three-dimensional, like fermionic and bosonic systems, do not apply here. So it's a whole new set of rules that we're not very familiar with, and so that's really interesting. Yeah.
Well, how long is the life of such a particle? If it
Oh, well,
relates with itself? How
Of the
do you
Majorana
detect that?
particle?
Yeah.
So it's not. This is actually theory. That we haven't experiments to confirm this.
Oh.
So it's a long sought Majorana particle. We don't know that. That's what they're actually trying to find. So that's really exciting. Yeah.
What's the need of Majorana particle?
The need of it?
Yeah.
No, it's just really cool physics. Like,
Yeah. It is predicted.
huh?
It is predicted, yeah.
Yeah.
Not found.
That's what people think should happen. And in super, they're supposed to be. So the Majorana particle has been looked at mostly in the field of particle physics. Because it's like relativistic stuff. But I guess one thing that I wasn't explicit about is that this really exotic physics is available in a benchtop experiment. Bismuth selenide and topological insulator films are not that hard to fabricate anymore, and so people are just looking at it because it's just cool physics, and no one's found this particle before, so it's like, oh, exciting. A brief historical background on topological insulators. TIs were first theoretically predicted, just computations in 2005, and that was for two-dimensional systems, so what was called a quantum Hall droplet. And what physicists predicted was that there was a special state of the electrons, like I said, the spin-orbit coupling of them, and that created a pseudo-quantum Hall effect. For those of you who aren't physicists, the quantum Hall effect just means that the conductivity of the electron, the transport of the electrons, is quantized in fundamental units like Planck's constant and stuff like that. And so they had seen that before. It's not like the quantum Hall effect is a new thing, but they had only seen it in systems where you apply a magnetic field perpendicular to the material, to the plane of the transport of the electron. And what's cool about materials like bismuth selenide is that this quantum Hall effect is being seen with no magnetic field and at room temperature. So it turns out that the spin orbit coupling of it acted as a pseudo magnetic field, and so that was really cool. And so they were experimentally confirmed soon thereafter, like a year or two after. But 3D systems were not experimentally confirmed until 2008, and this was at Princeton. I just got cut off here, but the first alloys that they looked was bismuth and timonite. But the lattice structure of that was much too complex, so they went back to the drawing board and they realized that bismuth selenide, which is here, but you can't see it, bismuth selenide was a good candidate. And that was what my research was concerned with bismuth selenide. So here I want to draw attention to the link between graphene and bismuth selenide. The group where I worked at MIT has done extensive research on graphene. I don't know if you guys are familiar with graphene. No? Graphene is basically a two-dimensional system, two-dimensional gas. It's basically a sheet of hexagonally arranged carbon atoms that is only one atom thick. And graphene's been around for a couple years, but it was basically it was the main topic of the 2010 Nobel Prize in Physics. And so, again, condensed matter experimentalists are very excited about graphene because it exhibits very exotic quantum physics, but with the magnetic field and with the low temperatures, and they have these cool toys where they have really high magnetic field and really low temperatures, and you apply currents, and then you see how the electrons behave in the lattice. And so this is what the band structure of graphene looks like. And a band structure is basically the relationship between the energy and the momentum of the electrons in the lattice. And this band structure is characteristic of a metal. So graphene, yes?
How should I read and interpret this graph? I have the line there.
That's a really good question. This is the momentum, in the x direction of the electron, and this is the energy of it.
Why is it?
So in the lattice, I have. So this lattice is a two-dimensional object.
Yeah, right, because it's one atom thick. So the way it's read is that these graphs are used to determine whether something is an insulator or metallic, and based on whether these lines cross or not. The fact that they cross means that there's no gap. A gap is just like an energetic constraint on the system. That means like, if there is a gap, this is what a gap looks like, by the way. From here to here, if there's a gap, that means that an electron, in order to go from the valence band to the conduction band, for it to conduct, to transport, it needs to overcome a certain barrier. This means that there is no gap. There's no barrier. So basically, the electrons here are in a state of matter that is metallic. So there's perfect conduction. Is that okay?
No. Yeah, that's good. Is kx the crystal momentum or
just momentum on the x-axis? Like,
okay.
I wouldn't say. I'm actually not familiar with crystal momentum.
Okay, because the solid state.
Doug probably knows.
Are people still concerned about KX or have we moved on?
I think we've moved on.
Okay.
Okay. No. It's cool. No. So, but do you have a question about it? Yeah.
So, graphene is the nice person that everybody likes. So this is the one you're studying. So what makes this graph on the right better than the graph?
No. It's not that it's better. What it is like what I was going to go into next is that if you look at this band structure and then you look at the band structure of bismuth selenide at the surface. Well, here, by the way, I use the same graph for two purposes. So these black lines, and I guess you can only see it. These are black lines and these are blue. The blue represents the band structure of bismuth selenide at the bulk of it. So most of it. But here it's I guess that's something I didn't point out. What's cool about bismuth selenide is that it insulates in the inside, but in the surface state it conducts. And so you can see that here. Here, this is the surface band gap, and as you can see, it's metallic. There's no gap. And the inside, there's a gap. So it is an insulator. So there's a cool duality about bismuth selenide that it insulates and conducts at the same time, even though nothing changes, right? And so that's why bismuth selenide is being attacked with graphene-like methods. And right now I want to address the topology part of it because it's very important, and I can't ignore the fact that my title has topology in it in a map. I'm by no means an expert in topology, and I am not going to go into what it is. You guys are familiar with it. But I just want to comment briefly that, as you know, an object has an intrinsic topological invariant that is what characterizes that object, right? The transformation, the smooth transformation, and all this topology stuff. And so here we have a very physical, evidence of a very strange thing happening in matter. Like here, this knot is used to represent what a topological insulator is. And what you can think of as being knotted is the wave function of the electrons in the lattice. It's being knotted in such a way that it behaves this way, that it conducts at the surface, but it insulates on the inside. So these surface states are topologically protected. That means these surface states have an inherent topological invariant, right? That makes the electrons of the surface conduct. This is the representation of the electron's wave function in a normal insulator. Different from a topological insulator. Right? And so I think what's relevant is that because it's inherent, it's invariant, all these things, you can't chemically dope bismuth selenide flakes so that the transport that you see in the surface of bismuth selenide is inherent to the lattice. Like there's nothing you can change of it. It is what it is. Yeah.
I was more wondering if are these different topologies, or are they're supposed to be like a label